Assalamu alaikum. This is
Well,
I'm a student of computer system engineering and technology. So basically, this session is about training. So जैसे कि आपको पता है कि ओपन लेन की ट्रेनिंग जो कि है थर्सडे को स्टार्ट होगी हमारी. सो ओपन लेन से पहले एक वेरिलॉग का सेशन होना बहुत कि ताकि बच्चे जो कि अपनी चिप डिज़ाइन करने जा रहे हैं उनको एटलीस्ट इस बात का पता हो कि अगर उनको एक छोटी सी आईसी डिज़ाइन करनी है तो उसका बिहेवियरल मॉडल कैसा होना चाहिए. इनके अगर उसको डिफ़ाइन करना है कि 2 इनपुट के ऊपर मेरा क्या आउटपुट आना चाहिए. सो बेसिकली दैट्स ऑल यू कैन डू इट इन वेरिलॉग. सो हमारे साथ वेरिलॉग की ट्रेनिंग में मौजूद हैं डॉक्टर हबीबुल्लाह जमाल साहब जो कि सीनियर फैकल्टी मेंबर हैं, VLSI डोमेन में एक्सपर्ट हैं और ही इज़ बेसिकली ए वाइस चांसलर ऑफ UET Taxila since 2001 from 2009, and basically he's serving now in GIK in electronics department. So Assalamu alaikum Dr. Saab. Hello.
वालेकुम अस्सलाम.
जी डॉक्टर साहब, आपको आवाज़ आ रही है हमारी?
आपकी आवाज़ आ रही है, मुझे आपको मेरा वालेकुम सलाम सुन रहा है कि नहीं सुन रहा है, ये बात है.
जी बिल्कुल.
प्रॉब्लम मेरी तरफ से हो रहा है ना. अब आवाज़ आ रही है मेरी?
जी सर, बेहतरीन आ रही है.
अब मैं शुरू करूं? May I start now?
Yes, बिल्कुल.
Bismillahirrahmanirrahim. Sorry all of you for delaying this session, but let's hope it continues nicely till the end of the session. So I have already been introduced to you. So I did my PhD from University of Toronto in 1982. I designed switched capacitor filters for my PhD. I fabricated them on a Vero board by wire wrapping or breadboard. I was interested just to confirm the performance of my circuits on the chip also. So I fabricated IC chips also in using the University of Toronto facility. Just to inform you, at that time in University of Toronto, the technology was, you can say 10 micron, 10 micrometer. Now you are talking in nanometers. At that time, it was 10 micrometer technology. There was single channel, and the aluminum gate was used for aluminum was used for metallization also, and as a gate metal also. And at that time in the industry, we had CMOS had come up against the other technologies. CMOS was considered and was established. And at that time, the industry standard was 2 micron, 2 micrometer. But the people at that time, they were really aware of the future. So that's why a book written in 1980 on VLSI by Mead and Conway, he used lambda as a feature size to define the layout of the diffusion mask, metallization masks, and other mask dimensions. And he claimed at that time that as the feature size is shrinking, so I'm just taking anything lambda, and now we know that this lambda from 2 micrometer has gone down to nanometers. So this was the state of affairs in 1982. And then at that time, the concept of computer-aided design was coming up, but was not really in use. In research, people were talking about that this is kind of thing which is going to happen. So this Verilog was developed in mid-80s, and simultaneously there was another language, VHDL. This Verilog, HDL, and VHDL. VHDL is a very large So it's HDL. Is the I have forgotten the exact Kikiji, what it is abbreviation, what it stands for. But today I have been asked to say something about this language, Verilog. Verilog is a language to describe hardware, and I will explain its basic concepts only by giving you a few examples. The material I have taken from a undergraduate book, Digital Design with an Introduction to the Verilog HDL by Morris Mano and Saletti. The copy I have is 2013 printed PDF file I have. So most of the material you will see I have taken from that book, unless one or two figures I have taken from the other book of the Morris Mano. So Verilog, I once again repeat, is just a language to describe hardware. The Verilog is similar to C. It is based on C. VHDL was based on ADA, but in public, Verilog became very popular because it was based on C. So mostly people knew C, so they automatically adopted this Verilog. The only difference is that in Verilog, in C, the instructions are executed in a sequence. You start from the first instruction and execute it and go to the second, third, and fourth. While in hardware, we all know that whole of the circuit, whatever you have put on a circuit board, is simultaneously on. So all of its components, maybe logic gates or whatever, they are simultaneously or concurrently, they are operative. So that is also the property of Verilog, that all of its constructs, they start at time, whatever is the simulation time t equal to 0, simultaneously. So while designing things, you must know this, that the sequence of instructions is not important, because all these instructions, they are simultaneously being conducted. To start it, if it doesn't disturb you, okay, are you still seeing the screen? I mean, it will.
Dr. Jamal,
Yes.
I guess your slides are not moving.
Okay.
Kindly,
Okay.
can you go back to, I mean, can you stop slideshow?
Sure. Okay. 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 No problem. Okay. I'm back.
Okay, now
So,
these slides are
okay.
changing.
Okay. Not here. Okay. Fine. So I am at slide number 3, where I have shown a simple circuit. And this circuit is again taken from the textbook I have mentioned. And the code written is also taken from the same book. And here you can see there is a circuit which has got change नहीं हो रही, थर्ड नंबर स्लाइड नहीं आई.
यस सर, हमारे पास आ रही है.
आ रही है, वो कहता आ रही है. हाँ, ये ना छेड़े इसको, क्या जहाँ. अब थर्ड स्लाइड है मेरे पास, जिसमें मैंने वो आई हैव शोन ए गेट, लेकिन हाँ, यस, this is a circuit which has got 3 gates, and, or, and not. These are the 3 gates with which you can design any combinational circuit. So this is a very simple circuit. How we will describe it? Every gate will be described as a gate. And to describe, for example, AND gate, you have a keyword AND. This keyword AND, for example, I'm showing here. Are you seeing my cursor? And okay, and my cursor is being seen by you or not? And
No sir.
no, and there is AND gate, there is AND statement, and I'm showing my cursor on it. Cursor नजर आ रहा है? Arrow फिर तक चलता नजर आ रहा है? Okay. So this and, which is written in bold, is the keyword. And in Verilog, when you write and, it means you are talking about an and gate. And similarly, there is a not is keyword, which simply tells the inverter gate. And or is again a keyword. Keyword means it is reserved word of the Verilog, and it has got only specified meanings. Here I am showing and, not, are three gates and their corresponding keywords, and these are sometimes called primitives. And then there is a style that in these gates, uh, he has given the number also. These are called substance names, instance names. So he has set gate, and gate has given the name G1, and then there are three letters W1AB. W is the output, W1 is the output, AB are two inputs of this AND gate. This is specified in the primitive that they will be written in this sequence. Output would be first one, and the inputs will be then will follow later. And this input output will be enclosed in the brackets. Similarly, for invert, the output is E and input is C, and you can see this correspondence in the diagram also, that the E is the output and C is the input, and this is modeled as not E output, C input, and G2 is instance name. Similarly, you can describe R. So this is the description of the three gates in this used in the circuit, and this circuit as a whole you can consider it as a block, and in Verilog we have a name fixed for it, again reserved name, keyword, module, and then this is the module declaration. We are going to declare this block as a module, and the name associated with module is given to the simple circuit. And then in the brackets we have the port list A, B, C, D, E. You can see here, this is our total block. This is our total block. A, B, C, D, and E are the 5 ports. D and E are the output of this wire. So as far as the rule is concerned, a module starts with the module keyword and ends with end module. There is no semicolon at the end module, but there is a colon in every other instruction of Verilog. So this is the concept, basic concept. For example, here I have described a circuit on the gate level, at the gate level. And now here we have just talked about gates, and in real life we know. Slide change हुई है? Slide change हुई है?
नहीं डॉक्टर साहब, स्लाइड नहीं चेंज हुई. काइंडली आप
Okay,
स्लाइड शो से खत्म करें.
अब स्लाइड चेंज हुई है कि नहीं? चलो और तरीका देखता हूँ मैं.
नहीं, अभी भी चेंज नहीं हुई.
शेयर और इसी को शेयर, इसी पर क्लिक करें और शेयर. अब जाए इसमें.
अब ठीक है जी. Are you seeing my fourth slide? No.
जी 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 डॉक्टर साहब, यू कैन कंटिन्यू प्लीज. डोंट मेक नो नो डोंट.
यस
अब भी ठीक है.
यस सर, अब स्लाइड शो हो रहा है.
Okay,
जी
now it is the same simple circuit, but we as all know that in real life, every gate has associated with some delay. So how to model the delay of a gate? For this is another module which we have written, and we have the name given to this module is simple circuit propagation delay. So it means it is the same simple circuit, but we have included propagation delay in it. And A, B, C, D, E, they are again port list is the same. The only difference is that now here when we have defined and, then there is a hash sign and in brackets the number 30. So it means we associate with this gate G1 a delay of 30 nanoseconds, or 30 unit is the unit of the machine itself. But we can define at the very start by using a compiler directive time scale with this backquote to start with, and then 1 nanosecond is the unit of measurement, and 100 picosecond, that's 0.1 nanosecond, as the precision. I mean, internally, the tool calculates the values every zero point 0.1 nanosecond, but displays the values after every 1 nanosecond. So here we say there is a delay of 30 nanoseconds in the gate G1, which is AND. Invert takes 10 nanoseconds delay, and OR gate takes 20 nanosecond delay. So that is how we can incorporate gate delays in our model. Change हो गया कि नहीं? हो गया change?
जी सर, हो रहा है भैया।
जी जी डॉक्टर साहब
ये चौथी स्लाइड नजर आ गई है टेस्टिंग वाली?
जी जी प्लीज
Okay.
प्लीज कंटिन्यू
Okay, fine. Alhamdulillah. So now this was our circuit. मैंने इस वक्त यहाँ just to draw it, I have simplified the simple circle लिखने की बजाय I have just written M1. This is my circuit M1, and I want to test whether it works according to my specifications or not. So what we usually do it, we put the circuit on our circuit board. So this circuit is M1, and you can think of this TM1 as circuit board on which this circuit is built. And this TM1 is usually called test bench. So what we will do is we will put the circuit, and then we will apply the inputs at A, B, and C, and we would like to see the corresponding outputs D and D, and verify whether our circuit works properly or not. So just to test this circuit in Verilog, we usually write a module which is usually called test bench. So for example, here I have written a test bench module and T underscore underline just to tell KG this is we are writing test bench. You can write your any name. And then see here the circuit. The circuit. This is my circuit M1, which I am going to place in this test bench. And this process is called instantiation. We had declared a module, and now we have copied it. This name is the same as that was used in the declaration of that simple circuit. Then we have given M1 name to this circuit, and this is the instance, this is the copy, or you can say this is the actual circuit which have been placed on the circuit board or within the test bench. So remember, this is called instantiation of the module. Previously, we have declared the module as of the simple circuit, and now I am talking about here It is the same name, same port list. I will come on this port list little bit later, how in what sequence these ports should be described. But there is an instance name M1. So my simple circuit will now be called as M1 with the port names A, B, C, D. And this simple circuit is placed in another block, which is called the test bench. And we have given it name as test bench for M1. And now, to connect the inputs to A, B, C, we know that it will be a digital signal. It will be 0 and 1, and we should apply 0 or 1 according to our desire or requirement. And this 0 or 1 applied at the input should stay there till we have measured the outputs. So these inputs A, B, C should hold these values. And now if a variable, this is an input variable ABC, we desire it should hold the values supplied by the input source are specified by us, our Verilog constructs. So what we will do is we will declare these ABC as reg. So reg is a variable about which we know it will retain its value 0 or 1. It's a binary, as shown here. A, B, C are the binary input signals. They have value 0 or 1. They can be written into, but that will be remaining there, that will be retained there, that will be stored there till we come back and change the value. So that's why we have declared here that these are reg. A, B, C of our circuit are reg. Okay, so this is A, B, C are our inputs, but for testing purpose we have declared them as reg because we will be providing 0 or 1 as our inputs, and these should stay there till we have done our measurements at D and E. So you can see here the outputs of this circuit D and E are simply wire. Wire is a property that is permanently connected to a gate or to a circuit, and its value remains unchanged. It cannot be changed by the user. Its value is controlled by the gate itself. What is appearing at D is simply like a wire. Whatever is the output of G3, that will be appearing at D. And whatever is the output of G2, that will be appearing on E. So D and E are simply wires, and they are declared here as wires, wire D and E. But A, B, C inputs are declared reg because we are to apply values there and to be retained there. And now I have used another block enclosed with an initial and end, with a begin and end. This is initial block enclosed by begin and end. I will come into it again, but at this time, just it is sufficient to say that this is initial. So this block is active at time equal to 0. It begins as soon as you switch on your circuit or you switch on your simulator. So to start with, at the begin, what we do is we are writing A, we are giving a value of 0 to A. So this is interesting way of writing in Verilog. You want to write 0, but you don't write 0, you completely specify it that A is a single bit. This 1 means total bits in the variable, then tick, then B means it's a binary. So it's single bit element in binary with the value 0. Similarly, B is 0, similarly C is 0. So if you see in our simulation output, you will see that at time t equal to 0 nanosecond, you have set the value of A equal to 0, B equal to 0, C equal to 0. So this is what you have done by using this statement, A equal to, these are 3 statements. separated by semicolons, though written in one line, which is not important in Verilog. You write in one line or different lines. Then, after 100 nanoseconds, you come, what you do is you change A to 1 tick B1 to 1, B to 1, C to 1. So this is, you can see here, after 100 nanoseconds, you have changed the value of A from 0 to 1, value of B from 0 to 1, value of Z from 0 to 1. So this is what your initial block has done. Initial block, which was active at time equal to 0, so it has taken initially the values zeros, then after 100 nanoseconds, it converted the values to 1. So this is the waveforms you can see for A, B, C. This is simple. And now, what is happening within the circuit? It will happen whatever this your circuit would desire. See here, you have placed this simple circuit here. So when you applied 0, 0, 0 here, the output should have been 0 here and 0 here, but 0 here. But you see, if E should be 0, but here you are saying that E is not 0. Sorry, if the input is 0, the output should have been 1. But here in the output, you see that E is not 1. E is something between 1 and 0, is unknown. It is unknown because the simulator doesn't know what was the value of C previously. And it will take 10 nanoseconds, and we defined that the gate G2 has 10 nanosecond delay. So after 10 nanosecond delay, the effect of input 0 will appear at the output as 1. So you can see here, if you see the units accurately here, after 10 nanoseconds, the E has changed from unknown value to 1. And then it remains 1. It is simple inverter. It is simple inverter. It will remain 1 till the input becomes 1 here, C. And after 10 nanoseconds, this 1 will make the output go low. So this is the C output. This is its input C. And this is the output of the inverter. And this is exactly the invert of the input. So as far as D is concerned, the D has got 2 gate delays of the AND gate, of the OR gate, and you can verify that the waveform seen here will be exactly in conformation with what you have written. And then we have another initial, this was initial block, this is initial statement, and this statement becomes active at T equal to 0, and this hash sign is delay sign. So after 200 nanoseconds, there is a compiler directive $finish. It means finish the simulation. So you will see here at 200 nanoseconds, everything will be finished. Your simulator will close. And usually we call this statement as stopwatch, that this has provided a window of 200 nanoseconds starting from 0 to 200 nanoseconds. And you can see the variables, input variables, output variables during this interval. Okay. So far that we declared a module, circuit, whatever it was named. Then with port list CAB, we declared its inputs, outputs, and this module was instantiated here in other module, which is a test bench circuit. And we declared the inputs of our original circuit as Latch and the output as the wire. And this is the instantiation. And here I have done the instantiation in the same sequence as, with the same port sequence as was declared. Output was declared as first, then it was followed by A and B. Similarly, we have kept the same sequence in our instantiated module, which we have given the name M. Then we have the stopwatch, initial, some time, then it was finished. So this is what we have done briefly so far. So you can see here there's another um, parameter keyword. Sometimes in Verilog or in other languages also, we use parameterized code. It means here we have defined here parameter stop time 1000 nanoseconds. Later on, let's say someone is interested in stop time, let's say 200,000 seconds. Or, so instead of changing the code everywhere, what he will do, he will come back and simply change the stop time, and that change will be implemented throughout the file because it is defined as parameter as stop time. So instead of writing 1000 here, we have written stop time, and this is a parameter which in this particular case has got the value of 1000 nanoseconds. So this is simply how we build a circuit, declare a module, and we instantiate a module. Again, I have repeated, declaration is now clear. Should be module, name, port list, and the ports are declared within the port list in the Verilog, which is available nowadays, and in previously it was declared outside in the second line as the port declarations, and all the functional details then go within the module.
So I have described this half adder, its module using two gates only. Then this half adder, you can see we use two half adders and a name to each instance. This is HA1, this is HA2. These two half adders are used to build a full adder. These two half adders and a gate, the OR gate. So this is the logic, if you can see, full adder. And now here, this half adder is instantiated here with the name of HA1, this one, and the second, this
Sir,
half adder. हाँ जी,
आपकी आवाज़ बहुत कम आ रही है. Can you please speak louder?
अच्छा, अब ठीक है?
जी सर.
ओके, इंशाल्लाह. तो दो सेकंड इज हाफ एडर 2 HA2, ये हमारा इंस्टेंस नेम है, एंड दिस इज द मॉड्यूल नेम. सो ये दो आपकी इंस्टेंसिएशन हो गई है. ये दोनों half adders have been put in the file, and this gate G1 is here. And now I have here the instantiated by port sequence, association of ports with is in sequence. So इसमें originally में output S and C थी, input X and Y थी. तो उसी सीक्वेंस से आप देखेंगे कि S1 और C1 ये आउटपुट्स हैं, X और Y इनपुट्स हैं. और हाफ एडर 2 की एक इनपुट S1 है, दूसरी Z है. तो ये आप देख रहे हैं S1 and Z आर द टू इनपुट्स, एंड आउटपुट इसकी एक S है, और एक जो है इसकी आउटपुट वो HA2 की S है, ये वाली, और दूसरी इसकी आउटपुट जो है वो C2 है. दिस C2 विद दिस C1, इसको एंड करके हम यहाँ पे जो एक्चुअल कैरी है फाइनल वो जनरेट करते हैं. सो दिस सर्किट एज होल इज ए फुल एडर, and this is its description. So we can go and complicating it again and again. Next slide. Okay, now we can use four full adders to make a 4-bit adder. And here I have just shown few new concepts. One is the concept of vector. Previously we were saying input as 1 bit A, but now in the square brackets I have written 3 down to 0. It tells that the A has got 4 bits, A3, A2, A1 and A0, and each bit can be addressed separately. For example, this is A0, A1, A2, A3. So this is being used at the input here, A0, A1, A2, A3, and these are the parts of this vector input. We call it vector. Vector जिसको bus कहना चाहिए ना कि this is input bus. This is called vector in Verilog. So this is the input vector A, and its parts are A0, A1, A2, A3. These are shown here in diagrams. Similarly, you have B's, and similarly, you have the outputs. Output is again a vector, S3 down to S0. That's output sum 3 down to 0. So this is a new style of writing. Instead of writing S3, S2, S1, S0, we can group together and write them as a simple bus. So that will be easy when you will be dealing with 16-bit bus and 8-bit bus. So that will be this concept of modeling buses will become very handy at that time. So now you can identify everything yourself. See here, this is module ripple carry 4-bit adder. Output is a sum with 4 bits. Out carry C4 is a single bit output. Here, this is a style which is used in Verilog nowadays. That's you wherever you declare the ports, you simultaneously declare the port names or port whatever the port is, output or input. This you also declare within the port list. There no need to write again and again. And then you need to connecting wires C1, C2, C3. These are wire use declared as wire C1, C2, C3. So C1 is the output FA0, then C2 is the output of FA1. So this is the 4 instantiations. It means we used one, it would declared one full adder, and we have used 4 of them. We have copied them and are reusing again. So this is an example of hierarchical design. And now next please, next please. Okay, now as previously I have just was describing things in the gate level. This is called gate level modeling, but that becomes very cumbersome because you will see the large number of gates in circuits, so you cannot describe any circuit on gate level. So now I am going towards the easier description of our circuits. We can use Boolean expressions to describe our circuit. For example, our original circuit, it's D. If you want to define it's D, you need to describe 3 gates. So instead of describing in terms of gates, you simply say assign D, this keyword assign. This is called assignment statement. It means that the output is assigned a value after this expression has been calculated, evaluated. So you can see here, okay, you have A and B, and then I think इसकी ट्रांसमिशन में गलती हो गई है. यहाँ पे ये साइन इन्वर्ट सी के नॉर्मली टिल्डा साइन यूज होता है, and you have he has not shown here a bar. The bar is used for R gate. तो यहाँ से वो R gate नजर नहीं आ रहा. ठीक है जी, कोई प्रॉब्लम हुआ है. इस तरह यहाँ पे नजर आ रहा है बार. अगर यहाँ से देख लें. So there's another expression. The out is ORing of 2 inputs. One input is this, and the second is input is this, and there's this pipe sign, this line. This indicates that this is OR gate, and the input to this OR gate is coming from a 2 inputs, cell and A. This is this input cell A, and then cell. See, यहाँ भी ये ठीक बनी हुई है. Cell invert and B, cell invert and B. So this assignment statement, yeah, this simple Boolean expression explains this circuit, which consists of 4 gates, by simply one statement. If you are to describe this circuit on the gate level, next slide. So you need 4 gates. So instead of writing these 4 gates, just by a Boolean expression, you have described this circuit, which is in fact a 2-to-1 multiplexer. So there are 2 inputs, A and B, and select is the control or select line, and the output will be either A or B, depending upon which one is high, cell A or cell B. So this is your standard multiplexer. This standard multiplexer can be described just by a line which I have written in the previous slide. Next, please. Okay, now this is another alternate description of the same 2 to 1 multiplexer. Again, here this is also written by a one line. Assignment M out, assign. This is continuous assignment statement. We say it is continuous assignment that the output is continuously being updated depending upon the evaluation of the right hand side. Any of the variables, if the right hand side changes, a changes, this whole expression will be evaluated once again, and the result will be assigned to M out. And in this case, we have used a conditional operator, this interrogation sign, and this colon. And the variable before this interrogation sign is a Boolean variable 1 or 0. If this is 1, then the first variable a is the result of this expression. If this is 0, then the second b is the result of this expression. So depending upon select is 1 or 0, either a will go to M out or b will go to M out. So you can see this is the functionality of a multiplexer, that by select you can select any one of these two inputs a and b to appear at the output. So this writing is called data flow description. So I have gone so far by two methods: gate level modeling, data flow modeling. Next. So actually, I have already discussed this gate level and this data flow level. In data flow level, we have assign keyword, and this is continuous assignment statement. It is continuous because it is behaving like your ordinary gates, in which the output of a gate is continuously, is always depends upon the inputs. If input change, the output of a gate changes, and this assignment statement is doing the same kind of functionality. And now there's one higher level also. This is called behavioral modeling. Usually, we like to use mostly this behavior modeling because that makes our life much easier using this procedural assignment statements. There are two procedural assignments statements and keywords. Next. Okay, there is initial statement which we already used, if you remember, in our test bench. We ran that initial block in which we set the values of A, B, C at 0, number 1, and then after 100 nanoseconds, we went there and changed it to 1. So that was the initial statement, and we also used changed, so that was the initial block. If you have more than one statement, then it's called block, and then we enclose this block between begin and end keywords. But if it's a single statement, that's it, then it's a statement. For example, if you remember, we used in our test bench an initial statement. This was providing a stopwatch that was simply initial, and then we said kg delay for 1000 or sorry 200 nanoseconds, and then we said dollar finish. That was initial statement. So all the initial statements are blocks, and the always statements are blocks. They are all active simultaneously. The difference is the initial is executed only once. You start from here, reach end. For example, here if I'm interested to write the same half adder on in behavioral modeling, what I will do is I will put first sum and carry to 0 by using initial statement. And then the value of the output will be controlled by using always. Always statement tells me this is a couple of statements, sum and carry, which will be executed, and this will be executed again and again. Every time A or B changes, there is an add sign, and within the brackets, we call this as sensitivity list. If any of these variables change, this block is executed. It starts from begin, completed, reaches end, comes back, and comes to this control statement and starts waiting for, looking for the change in A or B. So these are two procedural state constructs which are used in Verilog, and initial we have already seen, and always we will see in the next slides. So next please. Okay, so this is a depiction of the same, our old friend, this multiplexer on behavior level. See here we have used, oh this has changed yeah during the transmission
I
review. Anyhow मैं ट्राई करूँगा इसको समझा दूँ. But anyhow, इसमें देखने वाली बात is simple. The simple is this कि जी we are using an always, and the three variables A, B, and select. If any one of the input changes, then if select equal to 1, so there was a comment. This double slash is comment sign. There was a comment which has blown up during transmission through multiple media. So it has gone up and has overwritten this last statement. But you can see this if select is 1, or you simply write if and select within brackets. This means the same. If select is 1, then A will go to the M out. If select is 0, then else will be executed and B will come to M out. So this is the behavioral description of 2 to 1 line multiplexer. Next slide. Okay, this is transmitted properly. So this is 4 to 1 multiplex, again using always block. And in this block, I have given a new concept, that is using the case statement, case block, case statement, okay, case and case. And what we do is, this is our 4 to 1 multiplexer. So 4 to 1 multiplexer means that the 4 are the inputs and 1 is the output, 4 to 1 multiplexer. And to select 1 out of 4, you need two variables, and these are called select 0 and select 1, and these are input variables, and here it is declared as 1 down to 0 as select vector. The input are the 4 inputs in 0, 1, 2, 3. They are declared as inputs, these inputs. And the output is M out. The M out has got another property, that it is reg. We want it be retained at the output. While if it's wire, it won't work, because if anyone here is on wire, you don't maintain things. So this is the module, and this is its port list and port declarations, and this is its description, and using a case statement. In case statement, we say select, and select in this case is two variables, 1 down to 0, S0, S1, and they are written here to take D 0, 0. If this is 0, this is 0, it means to take D 0, 0, then the output is N0. And if it's 0, 1, the output is input 1. This output will go at the output. I am sorry, I don't have the pointer, my pen. ठीक है, आपको pointer नजर आ रहा है, मेरा तो नजर आ रहा था. So then you have to 1 0, so in 2 जो है out पे गया, 2B 1 1, so in 3 जो है output पे गया. So this is how we use it, how we can describe a multiplexer on the behavioral level. Next. Okay, then so far I have discussed the combinational circuits, and now a few comments on synchronous sequential circuits. So first of all, in synchronous circuits, we need clock. How clock is generated? Clock is usually generated using initial statement. For example, here you can see there is initial, and this initial block, because multiple statements between begin and end. So what would you say is clock equal to 1 tick 0. Remember, there is no here sign in initial block and always block. They themselves know, okay, what to do. So clock is equal to 10 first to start with. Then we will be repeating 30 times. And after every 10 nanosecond delay, this clock will be inverted. So half time period of this clock will be 10 nanoseconds, and it will be repeated 30 times. So you will be able to see some 15 clock cycles by using this code. In this code again, you have initial statement, clock 1 tick 0. ये मेरे ख्याल begin and was not necessary, लेकिन बुक में लिखा हुआ था वही कॉपी हो गया यहाँ पे. And then we have initial 300. This is stopwatch. This goes for 300. And there's an always statement that after every 10 seconds, clock should be equal to invert of clock. So it means this is going for 300 nanoseconds, this whole process. After 300 nanoseconds, it will finish. If this finish statement is not there, the stopwatch is not there, this will be working for always, forever, till you come back and say, switch off your computer or switch off your simulation. Similarly, another style is initial begin clock 0, and then there's a forever statement. This is the same as always. After every 10 nanoseconds, invert the clock. So this is how we generate the clock. Next. So then we have D latch and D flip-flop. The D latch is not synchronous. It is controlled by only the D data input and the enable input, and the output always Q. And you just see always enable or D. Just see if enable is 1, then D goes at the output. And if enable is 0, then D remains unchanged. A Q remains unchanged. Whatever is the D, Q remains unchanged. ये effective ही नहीं है, ठीक है जी. So with change in enable RD, you will have the output Q change accordingly. So this is how we model a D latch. There is another always using always statement. Here what he's doing is, if we have enable D again, if enable, then D is placed at Q. If not, the Q remains unchanged. And now, after this D latch and D type flip-flop, D type flip-flop, you must have a clock because flip-flop is a synchronous circuit. Otherwise, its functionality is the same, but now it works under the positive edge of the clock. If there is a positive edge of the clock, this will be executed. D will go at the output, and if there is no positive edge of the clock, Q will remain unchanged. Okay, and sometimes we provide a reset also, and we control the D with negative edge, neg edge, or positive edge of the clock. So, and this is the if reset is negative, then it means 0 goes to output, else D goes to Q. So this is D flip-flop with additional reset. Next slide. Okay, now this is T flip-flop using D flip-flop. This is our usual circuit. So we have a D flip-flop with this exclusive OR included. And you can see we have instantiated DFF here. And this is a QDT clock. अच्छा reset यहाँ पे you are seeing reset, लेकिन diagram में reset मैंने show नहीं किया हुआ है. Simply put here reset. That will be included. तो इनपुट जो है ना T and clock है, simply T and clock है. Input is T and clock, not the reset, which I have not shown. अगर आप यहाँ पे if you add an extra input here reset, then your Verilog code is okay. लेकिन इसमें you forget about this reset, ठीक है जी. So anyhow, you can see here that the input to the D flip-flop in a T-type flip-flop, this D input comes from T input of the T flip-flop and the output of the Q with exclusive OR. Here, this exclusive OR is implemented using an assignment statement. DT is equal to Q exclusive OR T. So this is your T flip-flop using flip flop, D flip flop, and exclusive OR gate. And then next, then I have shown the JK flip flop. This is diagram face again from Morris Mano book. And how it's implemented here is simply instantiate this JK flip flop and this glue logic, thus describe it using this assignment statement. You can see here this J and Q bar, J and Q bar, AND gate, and here this is Q and K bar, Q and K bar with pipe sign. This is the OR gate. So this statement assignment JK, JQ, this simply describes this whole glue logic by single assignment. And this is the instantiation of the D flip flop. ठीक है जी, so that's it. The next, now sometimes you like state diagrams. This is the state diagram of a counter. It is a 2-bit input counter. The inputs are 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. These are 2 inputs. Here I've shown it here. Input is X in, and X in is defined. Where X in is defined here, the X in should have. Sorry, this is not X in. This is the state 0, 0. This is state 0, 1. This is state 1, 0. This is state 1, 1. Input is this 0. This is input 0. This is input 0. This is input 0. So let's say we are in state 0, 0, and the output is 0. If the input comes as 0, it stays here, no change in its state. But if input is 1, the state changes from 0, 0 to 0, 1. And the output issued is 0. So this is state, this is output after the slash, and this is the input which controls the movement of the state from state 0, 0 to state 0, 1. Now this state is declared as reg and 2-bit state, and the functionality of this state diagram is implemented again using case statement, which uses state as the selection variable and moves. Let's say it is at S0. If X in is 1, it will S1 will become the state, and otherwise S0 will be the state. So simply using a case statement, we have implemented this state diagram. So similarly, we can describe the finite state machines using this model. Next. Yes, then how we show registers and memories. So this is again, ओए ये क्या हुआ है, मुझे नजर नहीं आ रही है मेरी स्लाइड, वो उन्होंने मुझे किया है, ये तेरा कसूर है
जिशान
कर रहा हूँ, मैं एक्चुअली इसको ठीक करने की कोशिश कर रहा था।
किसको ठीक करने की कोशिश कर रहे थे?
वो जो आपकी स्लाइड में कुछ इश्यू था।
चलो कोई बात नहीं, हो गया, थोड़ा बहुत मैं ठीक कर लूंगा इंशाल्लाह।
जी सर।
ओके फाइन, बस इसी को रहने दें ऐसी जैसी भी है,
ठीक है सर,
मैं समझा दूंगा। सो ही इज अ रजिस्टर, एंड समटाइम्स रजिस्टर्स आर मेमोरीज आर इंटरचेंजेबली चेंज। शाबाशी, आपने ये कर दिया, प्रोसेसर जो चढ़ गया था उसके ऊपर। यहाँ मैंने दिखाया हुआ कि ये 8051 का जो है वो रैम का उसके एलोकेशन टेबल है। तो इसमें देखिए इसकी जो फर्स्ट लोकेशंस हैं, फर्स्ट 32 लोकेशंस, दीज लोकेशंस आर एक्चुअली used as register also, as register bank also, and they are used as memory locations also. And similar thing is in Verilog, that you declare RAM as a register or as a memory. For example, here you can see this is the reg. There may be how many bits. If it is 8 bits, then you will see 7 down to 0. Memory 1, and then you have their values upper to lower. For example, this reg 0 to 3, so it means this is 4-bit locations, and It is, sorry, it's 4-bit. Every register or every memory location has got 4 bits, and the locations are from 0 to 63. It is your choice. You can write 0 to 3 or 3 down to 0. 0 to 3 or 3 down to 0 is your choice. Okay. So this is another example of reg where you have set to only one bit reg memory. So, but it has got 5 registers. So these are 5 1-bit registers. So this is how the registers and memories are declared in Verilog. Next. Okay, this is a figure from taken Logic and Computer Digital Design Fundamentals by Morris Mano, Charles and Kime, figure 6.3. Usually, when teach computer architecture, I take this figure to start with. Okay, this is a simple digital system, and it has got 2 units, data path under the control of control input. Control unit, the control unit can be controlled by control inputs. They may be coming from a program, they may come in from some external device, I don't know, but there is a control unit. And then there is a data path. So, and then the control controls the data path and provides control signals. And from data path, you have signals such as status signals, because control sometimes need to know, okay, what was the output of our previous operation, and depending upon the control determines its route. So the output here, there, data output, and then the control outputs may be there if the system may be controlling some industry device, so putting some control outputs also, and similarly some data also may be coming from the environment. So this is your usual digital system, and in usually people design control system as an FSM, finite state machine, and for model a finite state machine, I have already given you a very simple example of a state diagram how it is implemented. And as far as the data path is concerned, it's mainly let's say arithmetic unit, things like that, and they can be implemented using your combination circuits, and there will be associated registers. They can be implemented as registers. So this is how the design is done. Sorry, the time was short for me to prepare. Otherwise, one of my students said कि जी सर वो 8051 का जो कोड है ना वेरीलॉग का वो नेट पे फिर रहा है. तो मेरा तो ख्याल था कि उसको लाता उसको ब्रेक करके समझाता कि हाँ उन्होंने ये लिखा है, लेकिन वो स्टूडेंट भी नहीं मुझे मिला काफ़ी अरसे से. तो और कोई जी शान जैसा लैक स्टूडेंट मेरे कंट्रोल में नहीं थे यहाँ पे छुट्टियों पे गया हूँ लड़के जाते. एनी हो जाए तो अच्छा है, नहीं हो जाए तो आखिरी स्लाइड है. मैं भी थक गया हूँ. हाँ हो गया, क्या हो गया, नहीं हुआ. हाँ
Zishan?
चलो कोई बात नहीं.
Hello, Zishan?
जी मैं कर रहा हूँ शेयर, एक सेकंड.
I can share if you want.
ओके प्लीज.
Can you check?
यस थैंक यू.
Okay, that's what I wanted to see. So this is the Morris Mano simplest risk-based design, and if you have seen, it starts this function unit, and in function unit, it determines number one, what instructions are to be executed. Add with carry, subtract without carry, with borrow or whatever you call it, invert or not. So what is the arithmetic instructions which will be implemented in this functional unit? So depending upon that, it designs a simple arithmetic unit, and that within that it designs the logic unit also. The arithmetic unit was simple. It can be used using combination circuits. In fact, if you are using any tool, for example, Xilinx, and if you want to build an ALU, so there are generic ALUs available within the tools. So you simply go there, and they will allow you to adjust the ALU. These should be number of inputs, and this should be the data bus, bit of the width of the data bus. This should be the functions. So the ALU units are really, they are ready made. So simply you have to tailor them according to your needs, or you can write your own code. So, and then there's a logic unit in this function block, and that logic unit is simple, very simple. He has used 3 or 4 gates because he is using only 3 logic instructions and or invert and something more, and then puts them a multiplexer at the in front of them and decides what function you need. And that for this function unit, what should be the instructions? For example, if I see this is a function unit, key instructions are 5, so it means there are 32 possible variables here. So there will be 32 instructions, arithmetic and logic, that can be performed by this function unit. And the Verilog code is very simple to be written for all of them. And if you are to write for registers, you can very easily do that. And you have to write for instruction decoder. Again, it's a logic block, logic circuit. You can write as a logic circuit also. And similarly, this register file can be written as a register file. I have given the code how to write it. So with a little bit more effort and seeing the books I mentioned in my talk and have written on my slides, you can dig more. I think that's what I wanted to say about Verilog today. It was just a chance for me. Uh, I was caught because when I promised, I thought I will ask some expert to deliver a lecture, but at that time I couldn't catch someone in such a short time, so I had to come myself in the picture. But I'm sorry, I really need to thank all the participants, though perhaps beard me. I'm a very slow teacher nowadays. I go very slow, and plus रही सही कसर जो है नेट ने तोड़ दी हर 5 मिनट के बाद 5 मिनट की break. So those who are, I really appreciate the patience for their participants for their patience if they are still listening to me. If they have gone and to the bed or are relaxing, no problem. They really have a right to do that. And then I'm thankful to organizers, especially Naveed Sherwani and my Zishan, smiling now, and Kashif, especially Kashif and I. They were in touch with me, and unfortunately, what has happened has happened. I think they should do is they should edit this talk and remove the portions which they don't like, and then just republish it. And then there were many supporters. I mean, sitting here in GIKI, my dean especially, Dr. Naveed Bhatt. He gave me a free hand yesterday. I was out of GIKI, sitting at home in Taxila, and writing this presentation. It was his courtesy to give me the leave of yesterday, and today I'm still sitting in GIKI. I came to GIKI thinking that perhaps that here will be better than that of my home, but the problem was there. Anyhow, sorry that we things happen like this. I hope in future every one of our team, those supporting me, they will do better. Here there was engineer Muhammad Sadiq and engineer Muhammad Wahar Latif. They did their best to give the good experience to the participants, but whatever is the output, no problem. That's the life.
Yes, sir,
Okay.
exactly.
Thank you very much. Subhanallah wa bihamdihi.
Thank you so much, sir.
Subhanakallah wa bihamdihi. La ilaha illa anta astaghfiruka wa atubu ilayk.
Thank you so much.
Yeah, no one is to ask any question. No one.
I think
I
there
think they
are.
should have either they should have understood very well, or they actually, it's a simple thing. He likes, everyone know it, I think. But it was just to make people together.
Yes,
ठीक है
sir.
जी, छुट्टी करें मैं फिर अस्सलाम वालेकुम। छुट्टी करूँ या बैठा रहो? किसी ने सवाल पूछना तो पूछ ले कोई।
आई थिंक अभी हमारे पास कोई सवाल तो नहीं है चैट में,
ओके,
लेकिन थैंक यू सो मच सर, आपने हमें टाइम दिया इतना।
ओहो,
और इंशाल्लाह हम लोग नेक्स्ट सेशन भी रखेंगे, तो इस सेशंस को हम लोग मज़ीद बेहतर करेंगे, तो इंशाल्लाह फिर आपको दोबारा बुलाएंगे।
that's it.
यस, एग्जैक्टली।
If the output is a digital one, For example, where it will be retained. Then sometimes we say also declare output as reg. But I believe that nowadays in new Verilogs, this difference of reg and wire is not important because the new Verilog takes care of the itself cares कि जी it should be wire or reg. अगर आप भूल भी जाए तो मेरा ख्याल है माफ हो जाती है. Yeah.
Yes, exactly. That is the functionality of system Verilog, which allows you to write the logic instead of reg and
Okay,
wire.
so you call it as system Verilog. मेरा
Yeah.
प्रॉब्लम बच्चों ये है कि मैं 82 में PhD कर चुका था, तो ये सारी लैंग्वेजेस बाद में पैदा हुई हैं
अच्छा
और
अच्छा.
उसके बाद मेरे पढ़ने का टाइम गुजर चुका था. जो चीज़ बच्चे पूछ लेते हैं वो देख लेता हूँ, बता देता हूँ, पढ़ता पढ़ता नहीं हूँ मैं. ठीक है.
Yes. ठीक है sir. Thank you so much.
Okay.
I think we don't have any other question.
Okay, fine. Thank you very much.
Okay. Thank you so much, sir, for joining us.
Okay, Islam.
Thank you so much. Assalam.
Thank you very much.
Okay. So काशिफ भाई,
Yes.
थैंक यू सो मच. आपने ज्वाइन किया, सेशन को होस्ट किया आपने भी मेरे साथ, और थैंक यू सो मच ऑल. ओके, अल्लाह हाफिज़.